access the lecture notes on your laptop while you focus online. While you focus on the board. So if you cannot see what I write on the board, please, somebody online, make sure you let me know. Is the person online hearing me now?
Yep, I can hear you.
Oh, thank you so much for answering. So the moment you are not seeing what I'm writing online, please let me know. Okay? So because the major work today is going to be online. Okay, so I want to welcome everyone to my lecture today. Today, the majority of the work is going to be online. I needed to focus, on the board. So we started continuous type probability distribution. So the work today, basically, even though we're going to start new distributions, but I still want to walk you through, I'm going to review exponential because there's a connection between exponential distribution and the gamma distribution. And there's a connection between the gamma distribution and the chi-square distribution. There's a connection between the chi-square distribution and the F distribution. There's a connection between gamma distribution and the beta distribution. So because of the fact that the distributions are connected, and that is the reason why I'm basically going to review I'm going to start my review on the exponential distribution. Okay, I wanted to be focused. If there's any area you don't understand, please let me know. Okay, so actually, what happened is this. We find ourselves in a world where we basically want to capture happenings in the world. Okay, and because the world is stochastic in nature, we need a knowledge of probability distribution. Why do we need probability distribution? Because happenings in the world is probabilistic. That's why we need probability distribution. Now, I'm going to start all the way from exponential distribution. Now, we use exponential distribution as a model for waiting time before the occurrence of an event. And of course, I review X follow exponential distribution with parameter beta. So f of x is 1 over beta exponential raised power days, s greater than 0, beta greater than 0. And of course, I call beta is, a rate parameter. Okay, rate parameter. Now, I said this distribution, exponential, actually model waiting time, okay, waiting time before the occurrence of an event, okay, before the occurrence of an event. Now, I'm going to give you an example now, okay. If I actually go to Chicago intersection and maybe an ambulance, okay, is waiting at the Chicago intersection to see the first crash. What is the essence of the ambulance waiting? So that they can take care of, they can quickly effect treatment. Of course, in that situation, the number of time they're basically going to wait before the occurrence of an event is what we're going to use exponential distribution in that regard. But let me tell you this. The exponential distribution has a memoryless property that I talked about the other time. Okay. If they got to the traffic or, intersection and there's no crash and they wait to see whether there's going to be force crash, okay, the time they've been waiting, okay, and the time they're going to continue to wait, okay, is actually independent. Okay, now because of that, which means we're actually assuming a constant failure rate here. Exponential distribution assume is constant failure rate, okay, which means it doesn't matter the time they have waited and the time if they wait for additional time, it doesn't really matter whether they've been waiting. Okay, now exponential distribution, like I said, model the waiting time, and of course we got the mean to be beta, okay, and we got the variance of x, okay, to be beta squared. Of course, the standard deviation is going to be the square root of that. Okay, now I now want to move from exponential distribution, okay, to the gamma distribution. What is the relationship? Oh, the relationship between them is just like the gamma also model the waiting time before the occurrence of events. But let me tell you, the difference is this. In exponential distribution, okay, how long am I going to wait before the occurrence of one event, just one? But for gamma, how long am I going to wait before the occurrence of not just one, so many events? Does that make sense? Do you remember what we did under the discrete type, where when you look at the geometric distribution and the negative binomial? The geometric distribution is going to tell you how many failures am I going to have before I record the first success. Why the negative binomial is going to tell you how many failures am I going to have before I start recording a good number of successes. The same way, the negative binomial generalized geometric distribution is the same way gamma distribution generalized exponential distribution. Therefore, the gamma distribution now is basically, it's going to be the generalization. So now gamma distribution, X follow gamma with parameter alpha beta. Now what we're introducing now is the alpha, right? When alpha equal to 1, then I go back to exponential. Then what does the alpha means then? Alpha will be the number of that event. Does that make sense? In exponential, how long am I going to wait before the occurrence of one event, just one? In gamma, how long am I going to wait before the occurrence of alpha is now going to be the number of that occurrence? So if I want to write the f of s is in that regard, it's going to be x raised to power this, exponential raised to power this, gamma alpha, beta raised to power alpha, s greater than 0, alpha greater than 0, beta greater than 0. Take a look at this. This is a gamma distribution. When I plug in 1 in place of alpha, it's basically going to give me exponential distribution. Now, right here, the expected value of s is basically going to be alpha beta, and the variance of s is going to be alpha beta squared. Do you know when you plug in alpha to be 1, okay, the mean and the variance of a gamma distribution will automatically give you the the mean and the variance of the exponential distribution. If I'm talking about in physics, there's something that we call radioactive decay. Radioactive decay. If I'm talking about more than one radioactive material, if I want to talk about the life expectancy of more than one radioactive material, then I'm going to apply gamma distribution because I'm talking about more than one. Okay, how long I'm actually going to wait before before 2 or more radioactive material will disintegrate. Okay, so we're going to use a gamma distribution, And alpha for that is basically the number of such materials. So if I want to use a gamma distribution, then there are two parameters that I actually need to figure out. Okay, I need to know alpha and I need to know beta. The alpha C rate parameter, the rate of the occurrence of the incidence, and your beta is the shape parameter. Okay, the shape parameter. Oh, sorry. The beta is the rate and alpha is the shape. Take a look at that. Okay, so which means if you introduce a shape parameter into the exponential distribution, you now have the gamma distribution. Now, if I have some patients, or maybe women with cancer, or maybe some patient with cancer, and maybe it's a terminal disease. So how long are we going to wait until the event of certain characteristics of interest for more than one patient? Then I'm going to be talking about gamma. But for one patient, I'm going to be talking about exponential. Now, do you now understand the difference between exponential and gamma? The two of them model waiting time before the occurrence of events, except that in exponential, before the occurrence of one event, that may be the first, if that's the first event, and the gamma, decays or occurrence. Okay, now, if I want to calculate probability that has to do with this, I give an example where to calculate the probability that has to do with this, we need to get the CDF. You remember, I'm going to take you now. When we're working with the exponential, okay, when X follow exponential with parameter beta, we have this guy. We have this guy. If I want to find the probability associated with this, I need to find the CD, if I get a CDF, I told you the other time, the CDF is just going to be that I derived the other time, that we got to be 1 minus this. Okay, so if this guy is the CDF, okay, the CDF of exponential, okay, is in closed form, is defined, right? So if I want to find the probability of S greater, okay, it's just going to be 1 minus this guy. So for exponential now, it's just going to be 1 minus this guy, right? So if you take a look at this, I'm actually just going to have this. So which means this is the probability of S greater in exponential, okay? But when you are talking about gamma, gamma does not have a closed form of CDF. If I want to find the probability, I need an incomplete gamma table because the CDF of gamma distribution is incomplete. The CDF of exponential is complete. You can actually do whatever you want to do here. Now, if you check this week material, okay, I uploaded a gamma table, gamma statistical table. You can check now. Okay, we're going to use that gamma statistical table in this class right now to solve a problem that has to do with gamma. Okay, so what I'm going to do, give me 1 second. I'm going to solve a problem associated with that now. Any question? Is there any question? If there's any question, please ask on on a different. Okay, go ahead. Okay, so that's I integrated this from 0 to x. 0 to x is the probability of x less or equal to x. So if you want to integrate this guy now, okay, it's going to be divided by that 0 to x. this guy cancel that guy, right? You got negative this guy from 0 to x. If you plug in x, you're basically going to have this minus minus. When you plug in 0, this is going to be 1. So you're going to be 1 minus this guy. You get it now? Okay. Now, that's a very good question. Give me 1 second. I think I prepare. Where did I? Okay. Now, let's say, for instance, I want us to solve a problem on a gamma. Okay. I want us to solve problem on the gamma. Now, let's say now we want to solve problem on a gamma. You know, I told you, let me make attempt to derive a, if I make attempt to derive the CDF of a gamma distribution, it's basically, we're not going to have a closed form like this. We're basically going to have, you know, an incomplete. Give me 1 second. Okay. I'm going to have, the person online, can you still see what I'm writing on the board, right? The person online?
Yes.
Okay. If you are no longer seeing what I'm writing on the board, please, like I said, let me know. I don't want it to be left out. Thank you. Okay, now, if I want to make an attempt, because if I want to find the probability with a distribution, I basically need to understand what is the CDF. Okay, now, if X follow gamma, right, with the parameter alpha beta, okay, the probability, the f of s is x raised to power this exponential raised to power this gamma alpha, beta raised to power alpha, s greater than 0, this greater than 0, and this greater than 0. If I want to find a CDF now, so I want to find the probability of s less or equal to s, which is an uppercase. I want to go from 0 to x, okay? Then t raised to power that, exponential raised to power that, okay, divided by gamma alpha, beta raised to power alpha dt. If I want to do this, if I first if I let y be t over beta, okay, what is the y dt? The y dt is going to be 1 over beta, right? So if the y dt equal to that, what is the y? What is the x? Or what is the t? The t is beta dy, right? Okay, the t is beta dy. Okay, and what is going to be the t? Here, our t is basically beta y, right? T is going to be beta y. Okay, now if I want to make this substitution now, the probability of x less or equal to x, okay, what I'm going to have, okay, instead of t, okay, and I'm actually going to have beta y, okay, raised to power alpha minus 1, okay, exponential raised to power that. So instead of the t, I'm having beta, the y, divided by gamma alpha, beta raised to power alpha. When you take a look at what I have now, okay, if I have this guy, okay, and y raised to power that, exponential raised to power that, beta, the y, divided by gamma alpha, that, okay, you're going to see that this guy, we cancel that guy, right? Then I'm actually going to have is 0 to x, y raised to power this, exponential raised to power this, gamma alpha, the y. Now, this guy here is what we call incomplete gamma function. The incomplete gamma function, okay, the only thing we can do here is to check from a table. Then I'm going to give you an example on how to solve that, okay, from a table. Does that make sense? So the CDF now is this guy, which means the probability of x less or equal to that is this guy. And this is incomplete gamma function. Then I need to figure this out, okay, from a table. If I want to solve, and that was why I gave you that table. And I wanted to solve a problem now using that table. So which means if this guy is this, if I want to find the probability, let's say for instance, if I want to find the probability of S greater than that, it's going to be 1 minus this guy. So which means it's basically going to be 1 minus 0 to X, Y raised to power that, E raised to power this, the Y gamma alpha. So if I want to find the greater than, now I want to walk you through an example now. If beta equal to 1/5, it's super easy, super easy. Now I want to walk you through an example now. Okay, let's look at the example now. Okay, if beta equal 1/5 and alpha equal to 10. Okay, if you're given this, of course, they are expecting you to use a gamma, right? If this guy equal to 1, that would be exponential, right? Okay, now the question they ask you now, okay, now in the question, what they say is this. Let me put the question. Can I clean this one? Okay. Now, if there's anyone who doesn't understand what we're doing, please ask question. This is not lecture. This is tutorial. I want to walk everybody through everything. I'm doing tutoring something now, not teaching. I mean, not lecturing. Okay, now the example is if X follow gamma, right, with parameter this, and you are given alpha to be 10 and beta to be 1/5, they want you to find what is the probability of S greater than 10 and what is the probability of S greater than 2. If I want to solve a problem like this, what am I going to do? If I want to find the problem like this, don't forget, remember an incomplete gamma. The incomplete gamma is what we derive, right? Okay, the incomplete gamma said the probability of X less or equal to X, now in the solution now, okay, equals 0 to X. Okay, Y raised to power this, the Y, gamma alpha. And don't forget that initially, looking at the distribution, you know, where we were deriving it the other time, don't forget that initially, when we are deriving this, we said that the probability of this guy is 0 to X, you know, T raised to power alpha minus 1 exponential raised to power T over beta gamma alpha this dt, you know, where we want to start, and don't forget we let that Y equal this, which means I need to get my T is beta Y, okay? My T is beta Y, okay? Now, if you take a look at Y, if you take a look at, you know, what is acting as T here, where T equal to beta Y is more or less like X, okay? Now, I want to find the probability of S, you know, greater than that, okay? Now, what I will first do is this, okay? So the range of Y, it should be this guy, right? So if I want to get Y, okay, it means I have to use 10 that they're talking about, 10 divided by, what is beta? 1/5. Do you understand that? So 10 divided by 1/5. So 10 divided by, so which is more or less 10 over 1 times 5. That's going to be 50, right? Okay. So that you understand what I mean? You know, what is Y? Y is this over that, and we have a new variable Y. The Y, the range of Y is what you have here. Okay. So now, do you already have that? Those of you online. Now, if I want to find this guy now, I'm going to use 50, okay, and 10. Okay, 50. I'm going to check 50 and 10. Although in this present table, okay, there is no of, let me see where I can see 0.9863. Give me 1 second, where we have, maybe we have it in this table. Okay, what I'm going to do, let me do the one of s greater than 2. Give me 1 second. I just want to confirm. Let me do this one first. Okay, now let's do this one first. If I'm doing this one now, what is my y equal to? If you want to take a look at this, my y will be 2 divided by 1/5, right? Because I want to, the range is not in the table here. So what is that? 2/1 times 5, that would be 10, right? Okay, you are checking 10 against 10. Check 10 against 10 from that table. What do you have? Does 10 against 10 give you 0.542? You have 0.542, okay. So which means if I want to solve, why is it I'm not getting this again? It is over that table, the table I provided. So if I want to do greater than 2, what I'm going to check from the table is going to be 10 here, okay, against the alpha equal to 10. Now, when I check that, the result is, do you have a 0.542, which is 10 against 10, right? So it's 0.542 when you now subtract. Your final answer is going to be 0.458. Any question? If I gave you, okay, go ahead. The table. Yeah, the table is, we call it the incomplete. Do you have it? You can open it. It's in the module. I put it in the module. Have you all confirmed? Do you see the table? Right, it's there. So the table, you know what you're going to see in the table? You're going to see x against alpha. Okay, but the x you are seeing is not x, is the new variable. Okay, so if you want to answer a question that has to do with a gamma, because gamma is an incomplete, okay, as the CDF is an incomplete, you're basically going to make use of the table. Okay, so that is how to go about all that. Okay, I want to go to any question on this, but the one, the other time when I want to do this, okay, when I go 10 divided by 1/5, that gave us 50, but 50 is not in that table. So if I want to ask the question that's over that, I'm going to give you a table that way, or I can ask you to make use of an online calculator. There's an online calculator for incomplete gamma function. Does that make sense? Okay, now I want to go into another distribution now that we call chi-square distribution. Let me tell you this, chi-square distribution is very, very useful. Let me tell you this, chi-square distribution is very, very useful for chi-square test. As any one of there are some distributions that serve as a territorial jurisdiction for statistical tests. For instance, if you want to test if there's a relationship between two categorical variables, maybe you want to test what is the relationship between level of income, or the level of education and the level of income. When you have two categorical variables, we normally use chi-square test. But how do you decide when you conduct a chi-square test? You need a p-value, right, associated with the test. Then you need, for you to be able to get the p-value, then you need a chi-square distribution. How is the chi-square distribution derived? Then I want to tell you now, chi-square distribution is derived from the gamma distribution. Now, if x follow gamma with parameter alpha beta, f of x is this divided by gamma alpha, then beta raised to power alpha. Do you know that when if alpha equal V over 2 and beta equal to 2, then we have a new variable, okay, a new variable that we're actually going to form now will be called a chi-squared with V degree of freedom. So if I want to write a new variable now, I'm actually going to have y V over 2 minus 1 exponential y V over 2 y over 2, okay, gamma V over 2 2 raised to the power V over 2. This is a chi-square distribution. The chi-square distribution was actually derived from gamma distribution. When we set the parameter alpha to V over 2, V here means degree of freedom. Degree of freedom. V means degree of freedom. And of course, this distribution is what we use to conduct, to take a decision, when you are conducting a chi-square test, where you are comparing two categorical variables. Now, if the mean of a gamma is alpha beta, and the variance of exponential is alpha beta squared, then the mean of the chi-squared, okay, is just, putting that for this. The variance of a chi-squared, is just V over 2 squared. So here, it means V here. The mean of a chi-square is V, okay? The variance of a chi-squared is 2V. So take a look at it. If this is gamma, this is chi-squared. Take a look at that. Any question? So which means we go from the gamma to chi-square. When alpha equal to degree of freedom over 2 and the beta equal to 2, we have a new distribution that we call chi-squared. And of course, we can have this is the mean, this is the variance, which means I derive the mean and the variance can be, from here. Does that make sense? And let me tell you this, if you have a distribution like this, I can ask you to show that the mean is this. How can you show that? Expected value of V, don't forget, you're basically going to use 0 to infinity. V, f value of y. So y, f of y, the y, when you work on this, you will end up in V. That's what I mean. When you work on the variance, you're going to end up in that. Any question? Now I quickly want to move to another distribution. So chi-square, I just told you what the chi-square distribution is all about. Now I want to move to F distribution. Okay, I want to move to F distribution. I want you to see the story. The story actually starts from exponential, right? To gamma to chi-square now. Okay, now I want to go to another distribution that we call F. And let me tell you this. How do I get, what is the significance of F distribution? F distribution. Do you know in statistical analysis? I said one of you have heard about ANOVA test, analysis of variance test. Has anybody heard about that? Yeah, analysis of variance. Analysis of variance is F test. And without this distribution, you can never take a decision regarding the F test. The ANOVA test, when you are comparing means in more than 2 groups. Okay, but how do we derive F distribution? We derive F distribution from 2 independent chi-square. Look at the story. Okay, now if you follow chi-squared, okay, with V1 degree of freedom, and V follows chi-squared with V2 degree of freedom, okay, now F distribution is going to be U over V1 divided by V over V1, okay, which means the ratio of 2 independent chi-squared is F distribution. Now, if we the formula now for the for the distribution now, if F follows, okay, if F follows if F follows F distribution, we're going to say with degree of freedom V1, V2. So what is what is G of F? The G of F is going to be gamma V1 of V2 over 2, V1 over V2 raised to power V1 over 2 divided by gamma V1 over 2, gamma V2 over 2. Then I'm basically going to have 1 plus V1 over V2F raised to power V1 plus V2 over 2. Take a look at that. This is F distribution. This distribution, we derive it from this, using this. So what we're going to do in the rest of the week, the chapter 7, is about how to use a first principle to derive a distribution from another distribution. So I'm actually going to show you how we starting from this, then we end up having this distribution. Okay, sorry, it's not complete. V1 over 2 minus 1, yeah. Okay, this is a complete one. Okay, now take a look at that. This is F distribution. Okay, now this distribution is what we use to model, if you want to take a decision regarding F test, where you are comparing means in more than 2 population. Maybe you want to compare the annual household income in different states. Okay, maybe you want to compare the annual household income in the Midwest, or you want to see whether the annual average income in the state of Minnesota is the same as that of the Wisconsin and that of Michigan, because you got more than 2 groups. When you're comparing means, you're basically going to use F test that we also call ANOVA test. And you are doing that within this jurisdiction, within the jurisdiction of the F, we call it F distribution. Now, let me tell you this. In law, if somebody commits an offense in the state of Minnesota, that person should be tried under Minnesota law. Now, a situation where the person is now being taken to another state for trial, even though the other state was able to establish the fact that the person committed the offense, whatever decision they take is going to be declared null and void because of the fact that the other state does not have a territorial jurisdiction. So what I'm trying to say in essence, if I want to conduct a chi-square test, I need a chi-square distribution. If I want to conduct an F test, I need an F distribution. Does that make sense? That's what I mean. Now, the last distribution I want to talk about today is the beta. Do you know what? That beta is my favorite distribution. And I'm going to tell you why. Because of the flexibility of the beta. Okay. And let me also tell you the beta distribution. We derive beta distribution from the combination of the gamma that I'm still going to show you in the rest of the week. That is what chapter 7 in the textbook is all about. Okay. Now, if I have a random, so I want to talk about beta distribution. When you look at other distributions we've been talking about, well, you'll be talking about O numbers, the module, O numbers, the module continuous and so on like that. But a beta distribution, okay, is module, a random variable within the interval between 0 and 1, which means it's module proportions. What is the difference between this distribution and binomial? Binomial can either take 0 or 1, like if you have a 1 trial, right? 0 or 1. But the beta distribution is talking about fraction. It is greater than 0, but less than 1. Let's see. X follows beta with parameter alpha, comma beta. Now the f of s is basically going to be this 1 minus this divided by beta, alpha, beta. Okay, this guy here, that guy is basically gamma alpha, gamma beta divided by gamma alpha plus beta. So another way, if I want to write this guy now, I'm actually going to do x raised to power this 1 minus x raised to power this. Then I'm going to have gamma alpha plus beta divided by gamma alpha, gamma beta. So what you see here, this is the beta distribution. Okay, so in the beta distribution, you got two parameters. The two parameters, alpha and beta, they are shape parameters. Alpha and beta are shape parameters. Let me tell you this. This is most flexible flexible distribution in statistics. What do we use this to model? Okay, if I want to know, the rate, the click rate of your advertisement, like the click rate, what is the probability that when you actually advertise either on YouTube, on social media, what is the probability that the audience will watch the advert? Okay, because they may watch it or not. What is the probability? What is the probability that the customers will have a conversion rate in terms of purchasing? It is not all customers that visit your website that purchase. If I want to model, what is the probability that more than 50% of the customers that visit my website will actually have a conversion rate in terms of purchasing? Or what is the probability that a particular president will win a second time in office? Then I can use a beta distribution. Okay, now the mean of a beta distribution actually exists. Okay, the mean. Now, when you take a look at this is looking like binomial. You can see in binomial, you're going to talk about the number of successes and the numbers of failures. We're also going to have the same thing here, except that the range of the random variable has to be greater than 0 but less than 1. But in the case of binomial, it's a whole number. Okay, now the mean of this guy, the mean of which I can ask you to show, the mean is alpha over alpha plus beta. For instance, if if the customers have, let's say, 90% chance of converting rate, okay, I'm going to set alpha to be 0.9 and the beta will be 0.1. So if I want to do the mean in that regard, it's basically going to be 0.9 divided by 0.9 plus 0.1. So which is still going to be 0.9. Okay, so the mean is the same thing as alpha divided by alpha plus beta. So take a look at that. Then the variance, we can also derive the variance. Now, if I quickly take you to the material now, I'm going to show you what I'm basically talking about. Give me 1 second. So you should be able to know what distribution does. You get what I mean? We should be able to know that. Okay, we should be able to know what to do. Okay, so let me just okay, now I will quickly take you to what I'm trying to say. Okay, this is what I'm saying now. This is the beta distribution. This is the mean. That is the variance. Okay, we can actually derive all that variance. If I want to go through an example, I can also ask you to prove a square value of x equal to that. Okay, how do we actually get that? There's something I'm going to mention quickly. We also have, in the case of gamma, we have an incomplete gamma. We also have an incomplete beta. Okay, but let me tell you that we have a beta function. Okay, the b of alpha beta is 0 to 1 s raised to power this 1 minus s raised to power this ds. Okay, this is integral definition of a beta function, because we use idea of a gamma function in gamma distribution. You remember the other time when we're talking about integral definition of gamma, integral definition of the non-integral definition. We also have the same thing for beta. So this guy is the same thing as gamma alpha, gamma beta divided by gamma alpha plus beta. The whole of this is the same thing as this guy. So this guy is non-integral definition, non-integral definition, and this guy is the integral definition, is integral definition. Okay, so if let's say for instance I want to show the mean, I want to show that the mean is that I want to look up now. I want to find the expected value of s, 0 to 1. Don't forget the range is 0 to 1, s, f of s, ds. So I'm going to have is 0 to 1, x. What is f of s? So x raised to power this, 1 minus s raised to power this, ds. Then b of alpha beta. If I want to, how do I integrate this guy now? I wanted to look up now. I'm going to use the idea of a beta function to be able to do something here. Now, when you take a look at this guy now, I can combine this guy. That is going to be 0 to 1, s raised to power alpha, 1 minus s raised to power beta minus 1, b of alpha beta dx. Now, take a look at this. If this one can be written as b alpha, what am I doing? If you add 1 to this, alpha. If you add 1 to this, beta. Then for extra credit, what can I call this? Can somebody tell me for extra credit? If I want to write this in terms of a beta function, what am I going to have? We're here now, right? Can somebody tell me? For extra credit, this is where we are now. Expected value of s equal. So what will this guy become? Yeah? Good job. Send me a message for extra credit. So I'm actually going to have alpha plus 1 beta divided by alpha beta. And what is the non-integral definition? If I want to, this one is this one. So for this one, it's going to be gamma alpha plus 1, gamma beta, gamma alpha plus 1 plus beta divided by, for this one, gamma alpha, gamma beta, gamma alpha plus beta. I only need to simplify that. How many more minutes do we have? Like 4 minutes, right? Oh, it's over? Oh, we got to go now. We got to go now. I'm going to continue next time. We got to go now. We got to go now. We got to go now. Okay, see you next time.